Welcome everyone, and today's seminar speaker is Dr. Wangsawijaya, and they earned their PhD from the University of Melbourne, as you can see from her first slide, where she worked on turbulent boundary layers, in particular heterogeneous roughness. This was the topic of her PhD. And now she is a postdoctoral fellow at the University of Southampton, working with Bharat and Balasubramanian. I'm not sure if you're going to tell us a bit also about what you're doing in Southampton. Maybe, okay, good. Well, last week we have seen what happens when we have heterogeneous roughness in the streamwise direction, whereas this week we're going to see what happens when the roughness is heterogeneous in the spanwise direction of the turbulent boundary layer. You will see that the result is a flow which is completely different, and Dea is going to tell you more about this. So the floor is yours, Dea. Thank you.
Okay, thank you, Davide. Okay, hi everyone. My name is Dea. Currently postdoc at Southampton. Today's talk is going to be about roughness, same as last week. So roughness is something that is very common in engineering applications. So if you think about it, this is not desirable usually because roughness translates into drag usually. So when engineers estimate or they try to calculate drag of a rough surface, the calculation is made with the assumption that the roughness is homogeneous, as in it is equally distributed across the surface. However, as you can see in this example here, this is a fouling in the ship hull and turbine blades. The roughness is heterogeneous, as in some part of roughness might be smoother than the other, some other part might be rougher than the other. Or in this way, we can say that the roughness is heterogeneous. And this is not an example that is exclusive to engineering application. If you think about nature, especially atmospheric boundary layer, then we can think of the interface between ocean and land, or crops or city landscapes as heterogeneous roughness, with the turbulent boundary layer, the atmospheric boundary layer, developing over it. Of course, there are infinite ways we can arrange heterogeneous roughness, but for this talk, I'm going to talk about a very specific type of heterogeneity, where the roughness is heterogeneous in the spanwise direction, as in you have this streamwise aligned, spanwise periodic different strips of roughness. We are interested in the geometric properties of this type of roughness. So I'm going to introduce S. S here is the size of the roughness patch, or the width of the strips. Because this is because boundary layer develops over it, I'm going to normalize S with delta. Delta is the boundary layer thickness. This type of surface is known to induce something special. It's called secondary flow in the form of counter-rotating streamwise vortices. If we are going to be specific about it, this is the secondary flow of the second kind. This is a distinction that was made by Prandtl. The second kind is the secondary flow that is induced by turbulence. So this brings us to the first part of the question: is the secondary flows a function of S on delta, a function of the geometry of the surface? And if we look at this flow field of the turbulent boundary layer developing over this type of surface, the secondary flow shows up in this time average, in the mean flow field. However, if you look instantaneously, then we'll see that the secondary flows are characterized by elongated low speed, high speed streaks, which is not really unsimilar to the large scale motions or very large scale motions, LSM, VLSM, that is naturally occurring over a wall-bounded canonical wall-bounded turbulent flow. So you can see this in the smooth wall as well. So if you think about them, they're kind of similar. Both are characterized by roll modes and elongated streaks, both meanders as well. However, the secondary flows that comes out of spanwise heterogeneity, they show up in the time average velocity field. The one is in the canonical wall-bounded flows, as a smooth wall, they don't show up in the mean. So this brings us to the second part of our talk and the questions. So what are the similarities and differences between the secondary flows and the naturally occurring turbulent structure, particularly LSM and VLSM. So when I say secondary flows in this talk, I'm talking about the one that is induced by spanwise heterogeneity by the surface condition. And if I say LSM or VLSM, this is the one that is naturally occurring turbulent structures in the canonical wall-bounded flows. And getting back to the first part, both of these things, both LSM and secondary flows, they meander. So we want to know whether this streamwise unsteadiness, meandering is, you can consider that streamwise unsteadiness a function of S on delta. It's going back to part 1. And also, the final question that we want to answer is whether, if there is a scenario where the secondary flow and the naturally occurring turbulent structures, the LSM, can coexist with each other. So to answer these questions, we have a parametric study. We have 5 different surfaces with different S on delta. S is the width of the strip, so we have a very large strip and we have a very small strip, such that we have a range of S on delta bar. Delta bar here is a spanwise average boundary layer thickness. We have a range from 3.6, so this is large, to 0.3, which is very small. As a reference case, we have a smooth wall. These surfaces are laid down inside the open-ended boundary layer wind tunnel at the University of Melbourne. There's the surface covering the entire text section of the wind tunnel. The surface we made from strips of cardboard. This is the smooth surface, and the sandpaper. This is the rough surface. So if you see a white patch here, that's smooth. Black patch throughout this talk is the rough surface. We try as much as possible to equalize the height between the cardboard and the sandpaper, so that we know that the spanwise heterogeneity in this surface is induced by spanwise variation in the wall shear stress. So downstream of the boundary layer strip, we set up a PIV, cross-plane stereoscopic PIV measurement. The RE tau, the Reynolds number based on physical scale, is about 2000. For the smooth wall, it's quite a high Reynolds number. We have a cross-plane stereo PIV. We've got a flow field. The field of view is about 4 delta times 3 delta. And to capture the streaks of the turbulent developing over the surface, we have another wall parallel plane PIV. The field of view is stitched from 3 different cameras, and the total size of the field of view is 5 delta times 9 delta for the smooth wall. We would like to capture the secondary flows. We set up the laser sheet exactly at the center of each secondary flows. So for smooth wall, we set the laser sheet into 2 different planes to accommodate the changing size in the secondary flows in the heterogeneous roughness case. So the PIV that I'm showing you here, they're not time resolved. So we've got another set of measurement. This is hot wire anemometry on a 2-dimensional grid in a spanwise and wall normal grid. The boundary layer type probe, the probe is the boundary layer type, 5-micron wire. The type is Wollaston wire. So for every instantaneous velocity field, here we can decompose into time average or mean flow field, capital U, and fluctuation about this mean, U prime. Capital U, the time average velocity field, we can decompose further into its YT average, so time average, spanwise average, and U tilt. U tilt here is the time average spatial fluctuations. So if we think about this and say that U tilt is the stationary component of the secondary flows, because as you can see, there's a low speed, high speed flow there. This is the stationary component of the secondary flows, and U prime is the affecting turbulence, and as we come to the end of this talk, is also the unsteadiness part of the secondary flows. Use another component, U tilt prime, which is the combination of U tilt and U prime, which this will come out later in this talk. But for now, let's see what happens in the mean velocity field. So this is the contours of streamwise velocity field, capital U, at the largest S on delta case. So this is the case with the largest strip. The contour is U, the secondary flow. I hope you can see it clearly. The secondary flow is shown by the contour of, by the vector of vector field of V and W. So this is, because of the size of the strip, I'm only capturing half of the secondary flows. You have to imagine this mirrored on the other side of the tunnel. So this is the secondary flow. The secondary flow is very close to the transition between the rough surface, here the black patch, and the white surface, the smooth patch. Further away from the transition, further away from the secondary flows, we can start to see that the contours starting to flattens. And we think this is what happens. So when S on delta is much larger than 1, so when the roughness strip is much larger than the flow depth, boundary layer thickness, then the secondary flow occurs near the transition between the rough surface and the smooth surface, and further from the secondary flows, the flow comes back to its homogeneous roughness condition. So the smooth strip behaves like a smooth wall, and the rough strip behaves like a rough wall. On the other extreme, where S on delta is very small, so S is very small compared to delta, we see that the contour flattens. So what happens here is that at this S on delta range, the size of the secondary flow is confined by the size of the strips. So a small secondary flows is confined near the surface, and above the surface, the flow reaches homogeneous roughness condition. Between these two extremes, when S on delta is either very large, very small, we've got a regime where S on delta is approximately 1. So S is approximately equal to delta, and for this case, the secondary flow, as you can see here, is space filling. We can measure the strength of this secondary flow that shows up, right? So, before that, so this is the 3 flow regimes that will come up very often in this talk. So S delta is very large, much larger than 1, approximately equal to 1, or much smaller than 1. I'm also going to introduce some locations related to the secondary flow. So when you see this label U, this is common flow up. This is where you see the mean flow goes up. C is the center of the secondary flows, and D is the common flow down. So this is where you see downwelling. This is where you see the flow goes down. You can measure the strength of the secondary flow. This is the mean swirl strength multiplied by the sign of vorticity. So you can see the direction of the secondary flow. We are measuring the strength of the secondary flow by taking the integration of this swirl strength in the areas surrounding the secondary flows. And if we plot this as a function of S on delta, we can see that the strength of the secondary flow is maximum when S on delta is approximately 1. So when the width of the strip is approximately equal to the flow depth, which seems to suggest that at this flow regime, the secondary flow is the strongest. However, this might not be the full picture. So I'm going to show you the spanwise-induced spectra. So this is the U prime, the fluctuating component of a smooth wall, and in the large S on delta case, and intermediate S on delta case, when S on delta is approximately 1. I'm showing you the spectrum, the contours of the energy spectrum multiplied by the spanwise wave number, so Ky, as a function of lambda y, the spanwise wavelength, and z. Z is the one normal location. This is for smooth wall, large S on delta case, and intermediate S on delta case. This is the spectrum of U prime, so the fluctuating component. And as you can see here, there are 2 things that I want to point out. First is that I didn't do direct measurement, so anything that you see here is normalized by U infinity. So for smooth wall, it has lower energy than the heterogeneous roughness, because the heterogeneous roughness has some sort of roughness. And the second thing that I want to point out is whether they're smooth wall or whether they're heterogeneous roughness, it seems that they peak at the same location. They reach the peak, the spectra, the energy spectra reach the peak at the same location. So approximately at S on delta equals to 0.2, and the lambda, the spanwise wavelength, is about 1. Spanwise wavelength is about equal to delta. This is the U prime, so the fluctuating component. When we take the spectra of U tilt is the spatial time average spatial fluctuation, or in the heterogeneous roughness case, this is the sign of the mean secondary. This is the sign of the mean secondary flows. Obviously, this is 0 in the smooth wall, but this is not 0 in the heterogeneous roughness case. But one thing that I would like to point out here, what's interesting here is that the energy for the U prime is higher in the large S on delta case, but the energy of U tilt is smaller in the higher S on delta case. In the intermediate S on delta case, S on delta equals to 1, this is the bottom one, the energy is smaller for U prime, but for U tilt, the stationary component of the secondary flow, the energy is very strong. So we can quantify this using integral around the peak. For the U prime, energy of U prime, the fluctuating component, it reaches minimum where S on delta is approximately 1, but the energy of the U tilt, the stationary component of the secondary flows, reaches maximum where S on delta is approximately 1. So there seems to be an interplay between the turbulence and the secondary flows, in the sense that maybe some energy is transferred from the turbulent to the secondary flow, or maybe something else. I'm not sure at this point, but there seems to be an interplay between them. So this is not new. This has been discovered before, this kind of interplay between the turbulence and the secondary flows in the open bed, rough bed open channel flow, and the square duct flow. Simple interpretation of this is this. So this is U prime, which is the fluctuating component. And this is U tilt, which is the stationary component of the secondary flow, which, as you can see here, has a very distinctive spanwise mode and infinite streamwise mode. Taken together, they form this long low speed and high speed streaks, which seems to be very much locked in place for this intermediate case. So what happens here is that this thing, S on delta, might be the measure of how well the turbulent structures is locked in place by the surface. The locking seems to be most effective when S on delta is approximately 1, which is the case that I'm showing you here, where you can see the structures being locked by the surface. However, I would also like to point out that as they are very well locked, they are not stationary. These structures meander. This meander we can actually show and measure. So I'm going to show you the streamwise energy spectra now. So this is the energy spectra of U prime, the energy of U prime, from multiplied by Kx. Kx is the streamwise wave number. This measurement is coming from the hot wire anemometry. So I'm going to show you, this is the contour of streamwise energy spectra. At the center of a smooth patch as a function of Z, the one normal location, and lambda x, the streamwise wavelength. So this is at the center of a smooth patch, and we have other locations all the way across the adjacent rough patch. So it's really difficult to see anything from here. So I'm going to show you the isosurface of the energy spectra. So this is our function of spanwise location, one normal location, and streamwise wavelength. So this is the spectra for the intermediate case when S on delta is approximately 1. As you can see here, there's this extra bits of energy at the location of the secondary flows, and the wavelength of this extra energy is between 3 to 4 delta. We're integrating this, so we want to quantify whether this is a function of S on delta again. And eventually it is. So the extra energy that we discover here at 3 to 4 delta is maximum when S on delta is approximately 1 at the intermediate case again. This is the sign of meandering. So to conclude the part 1, we can see that secondary flows is a function of S on delta. The size of the strength and the strength of the secondary flows is a function of S on delta. Maximum when S on delta is approximately 1. Spanwise locking is most effective when S on delta is approximately 1. And we discovered that there is a streamwise unsteadiness, which is very strong. It's strongest at S on delta approximately 1. So this brings us to the second part of the question, the meandering, the streamwise meandering that we discover here. They are a feature of both LSM and the secondary flows. So what are the similarities and differences between the secondary flows and LSM that naturally occurs in wall-bounded flows? To do that, we are going to compare. This is the wall parallel plane. of U prime from smooth wall and the intermediate case. So this is the cases where S on delta is approximately 1. I'm going to filter this, and I'm going to extract each and every low speed structures that we detect here. As you can see here in the intermediate cases, the structures are very well locked around the common flow up in this case. And I'm going to extract a spine in each and every one of these structures from smooth wall and the intermediate cases. And I'm going to do a conditional average in the minima of these structures. Here, if you look at it from the cross-plane view, this is where the turbulent structures leans furthest to your right. Going to take another conditional average at the maxima. This is where you see the structures leans the furthest to your left. If you look at it in a smooth wall, this is the result. This is the conditionally average U prime. The minima, when you take the conditional average at the minima, this corresponds to positive V prime. V prime is the spanwise fluctuation. You take it at the maxima, this corresponds to negative V prime. V prime, again, is the spanwise fluctuation. We need to know this because for the cross plane here, we can't really detect the structure, so we have to use other conditional average, other conditions for conditional averaging, which in this case we take it at low speed event because we don't have the streaks. Take it at low speed events, either at positive V prime or negative V prime, and we try to get as close as possible to the wall. So if you look at the conditionally average, U prime, you can see that this is you have this feature, low speed structures flanked by two high speed structures. So blue flanked by two reds in the smooth wall. It's leaning towards your left or right depending on the condition of V, on the condition of the spanwise fluctuation. On your right, you see the same quantity, but for the intermediate case. So what we can see here in the smooth wall, you've got low speed flanked by two high speed structures, but I think it's the same for the intermediate case, but in this case, the asymmetry is much stronger. If we look at the wall parallel plane, we can see that the structure looks quite different because it meanders strongly for the intermediate case. And this behavior is persistent when we go to the next smaller S on delta, which is at 0.6. The wavelength we can estimate, the wavelength of this meandering, we can estimate is about 4 delta, which is what we see in the hot wire result. So with that, we can reconstruct, we can figure out how the structures meander for the smooth wall. This is the conditional average U prime from the cross plane. And this is the wall parallel plane. I know that these are not the exact same condition, but it helps us to work out how the structures meander. So this is the structures that we reconstruct from the conditional average for the smooth wall. And this is for the intermediate case. They look different. The intermediate case meanders more, definitely meanders more than the smooth wall. However, these structures, both of these structures, reminds us of the strict vortex instability model, which was initially developed for the near wall streaks, near wall model, but people have since discovered it in Lockwall, in the Locklow and beyond, so in much larger scale. So I think it's quite interesting that the secondary flow is induced by surface condition, in this case, spanwise heterogeneous roughness, should follow this kind of pattern, this kind of structures. So this is what happens when S on delta is approximately 1. So in the intermediate case, when we can see the secondary flow is filling. What will happen when S on delta is much larger than 1? So in this case, we've got secondary flows confined to the transition between the rough and smooth surface. Further from the transition, it reaches spanwise homogeneous conditions, so homogeneous rough or homogeneous smooth wall. So there is LSM there. So in this case, secondary flows coexist with LSM to know how to separate these two. So again, I bring out the smooth wall and the largest S on delta case. Same story, we detect the spines of each large scale structures, and we do conditional average in the minima and the maxima. However, in this case, for the spanwise heterogeneous roughness case, we have to separate which one is the secondary flows and which one is the LSM. So coming back from our previous conclusion that S on delta is a measure of locking of the turbulent structures of the secondary flows, then we can estimate that the secondary flows is locked, or in this case, the low speed structure is locked around the common flow up. So we can say that anything that happens, the red region here, red shaded region here, comes from the secondary flow. Anything outside that is the large scale motions from the homogeneous roughness. And we can say that let's just assume that the size of the width of this red area is twice the size of the secondary flows. Let's just assume that for now. Same story as before, we present the conditional average on the cross plane and the wall parallel plane. This is LSM for the smooth wall and what we assume to be secondary flows. If you look at it, there is still some asymmetry in the structures. However, definitely not as strong as the asymmetry that we see when at the intermediate case, where S on delta is approximately 1. The LSM detected from the smooth wall and what we assume to be homogeneous roughness from the largest S on delta case, they also look pretty much identical. And we can again measure the amplitude of this meandering of the structures. And if you look at it, the amplitude of the meandering of these structures is again a function of S on delta. The secondary flows, or what we assume to be secondary flows, reaches a maximum meandering amplitude when S on delta is approximately 1. However, at the very large S on delta case, the amplitude is similar between the LSM detected for smooth wall and what we assume to be LSM in the heterogeneous roughness, and what we assume to be secondary flows from the heterogeneous roughness. The amplitude is quite similar, so it's getting more and more difficult to differentiate which one is the LSM and which one is secondary flows. Same story for the very small S on delta case, where as you can see here, the amplitude is very similar between the secondary flows and the LSM detected from smooth wall. However, again, this might not be a full picture because for the smallest S on delta case, so the much smaller than 1, the secondary flows is small because it scales on the size of the roughness strip. After that, the flow reaches homogeneous condition. So we have to think about, so we cannot use the detection of LSM and secondary flows based on the spanwise location as we did before. We have to think about other ways to separate the secondary flows and the LSM. So to do that, I'm going to use a POD filter. I'm not going to go into details now, but with this filter, every instantaneous flow field, U prime, can be separated into the larger scale and the smaller scale. The smaller scale is anything that is what we assume to be the scale of the secondary flows, and smaller. The larger scale is anything bigger than the secondary flows. Story with the wall parallel plane, separate this into larger scale and smaller scales. Same story as before, we detect the structures, the long structures, and then we do conditional average on the minima and the maxima. So for the smooth wall and the smallest S on delta case, this is the conditional average from the what we detect as larger scales. They look identical. However, when we go to the smaller scales, you can see that the smooth wall and the smallest S on delta case, they're different. There is this spanwise periodicity in the smooth wall, possibly coming from the secondary flow that is not on the small S on delta case, that doesn't exist in the smooth wall, and the size periodicity is as the size of the roughness strip. So To conclude my talk, so we've tried to reconstruct the structures, the turbulent structures in the smooth wall and the secondary flows, where the secondary flow is approximately equal to delta. The structures meander more strongly. However, both of these structures are reminiscent of the vortex instability model, only they exist in much larger scale. In the case where S on delta is much larger than 1, the secondary flow, the LSMs detected from smooth wall and from the heterogeneous roughness, they're identical. The secondary flows still show some sort of asymmetry, but definitely not as strong as the intermediate case where they show strong asymmetry or strong meandering. For the smaller S on delta case, S on delta is much smaller than 1. The LSM is identical to the smooth wall. At the smaller scales, the secondary flows coexist with this LSM, and they are relatively undisturbed. So the analysis that I'm presenting here has been published. If you want to look into more details, there are some things that I haven't managed to answer yet. So at this regime where S on delta is approximately 1, S is almost equal to the flow depth. The secondary flows, as you can see, meander strongly, but they're also effectively phase locked by the surface. I have no idea how something that is very much locked also has the strongest streamwise unsteadiness, and I'm not sure why this should happen at this particular flow regime when S on delta is approximately 1. The similarities and differences between the secondary flows and LSM also poses another question on whether these two things share the same formation mechanism. This is possible. I think Townsend had this idea. This is possible because both of them, if you think of it, results from instantaneous spanwise variation in wall shear stress. Is just in the canonical wall-bounded flows. This phenomenon is chaotic. In the secondary flows coming from surface heterogeneous, spanwise heterogeneous roughness, they are persistent and they're forced by the surface condition. So there are still some questions that we should answer. Another thing that I would like to do next is that I only vary one parameter. In this case, just S on delta. I think it would be useful if we can explore larger parameter space. For example, Reynolds number. I only did this in one Reynolds number, so bigger Reynolds number, larger range of Reynolds number would be useful. And if we can test this on other surface geometry. So if you look at this picture, the right one is the type of surface spanwise heterogeneity that I'm examining here, which comes from the spanwise variation of the wall shear stress. However, there are other ways to incite the same secondary flows. That is, if you have something like ribs, you can see on the left, this is a rib-like structure where this spanwise heterogeneity is induced by spanwise variation in the virtual origin. So it will be interesting to see this in other type of geometry. The takeaway home message for this talk is that it's possible to manipulate turbulent structures with surface treatments, and you can see different arrangement, different parameters makes the turbulent structures behave differently. So there is a potential for flow control application here, which I haven't thought about yet, but this is somewhat related to the kind of things that I'm doing now as a postdoc in Southampton. So we're interested in the porous and rough surface problem because these two things, porous and roughness, porosity and roughness, they give two different effects to the flow. So porosity relaxes blockage, but roughness adds up blockage. We're not sure what happens if we combine those two. This is a porous surface of foam, a sheet of foam laid down inside a wind tunnel at the University of Southampton with a mesh roughness sitting on top of it. We're interested in the characterization and scaling. So roughness, we know that the characterization is very well known. We have delta U plus, the Hama roughness function, which is in some ways the measure of drag. We have K, the roughness size, or roughness height, and we have K as the equivalent sane grain. Porosity, there are known characterization as well. You can use a capital K, which is the permeability, or you can use H, which is thickness of the porous surface. But if we combine roughness and porosity, we're not sure yet what characterization and what scaling that might work, and whether we can decouple the effect of roughness and the effect of porosity on the flow. We are also interested in the aeroacoustic properties. So right now I'm setting up measurements. We've got a new wind tunnel commission at the University of Southampton. So with, for Smuto, IDTAU can go up to 15,000. We are still characterizing the flow, and we're also preparing for the measurement in the porous and rough surface. Other projects that I'm also involved in still involves another surface treatment, but now surface treatment is isolated. This is a cluster of tall, you can say it's a tall roughness or canopy. So if you have this cluster of cylinders with the incoming flow, the turbulent boundary layer is the incoming flow, there are ways in which this flow can escape from this canopies, cluster of cylinders. So either they escape from the top, or they escape from the side of the cluster, or through the trailing edge. We are interested in how scalar from the floor is transported across this obstruction, across this cluster. We're interested because this is somewhat related to pollution problem in big cities, where you can think of tall buildings, apartments, or skyscrapers, or office buildings as a cluster of tall obstructions, tall roughness, and you can think about the pollutants as a scalar. So we're doing this test of clusters of different densities, and we are doing simultaneous PIV and LIF plan, a laser induced fluorescence, to capture the scalar concentration. So we've got the simultaneous velocity and scalar data. The initial findings for this project is still under review, but the preprint is available on arXiv if you're interested. And right now we're just trying to work on the data, see the momentum scalar transport, and the dispersion model for this type of surface. So that's it from me, and I'll be happy to take your questions. Thank you.